Welcome to Cambridge IGCSE Physics, Lesson 34.1, Magnetic Poles and Forces. Today we explore the fundamental principles of magnetism, focusing on how magnetic poles interact with each other and with magnetic materials. This is core content for your Cambridge IGCSE Physics examination, covering essential concepts that form the foundation of electromagnetic theory. We'll examine the behavior of north and south poles, understand attraction and repulsion forces, and learn to use precise scientific terminology. These concepts are crucial for understanding motors, generators, and many modern technologies. Let's begin our systematic study of magnetic forces. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, describe forces between magnetic poles. This means explaining how north and south poles interact, including the fundamental rule that like poles repel and unlike poles attract. Second, describe forces between magnets and magnetic materials. This covers how permanent magnets attract materials like iron, nickel, and cobalt. Third, use terms N-pole, S-pole, attraction, repulsion. You'll use precise scientific vocabulary correctly in explanations and calculations. These objectives align with Cambridge IGCSE assessment objectives, AO1 for scientific knowledge, AO2 for problem-solving application, and AO3 for experimental skills. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, magnetic poles, which means regions of strongest magnetic force on a magnet. Every magnet has exactly two poles. Second, north pole, which means the pole that points toward Earth's magnetic north when the magnet moves freely. We abbreviate this as N-pole. Third, south pole, which means the pole that points toward Earth's magnetic south. We abbreviate this as S-pole. Fourth, attraction, which means a force that pulls objects together. Fifth, a repulsion, which means a force that pushes objects apart. Understanding these terms precisely is crucial for describing magnetic interactions accurately using scientific language. Let's explore our first core concept, magnetic pole interactions. The fundamental principle states that like poles repel, unlike poles attract. This means magnetic force acts between poles without physical contact, demonstrating action at a distance. The definition is, magnetic force acts between poles without contact through invisible magnetic fields. Let's examine the rules systematically. First rule, N-pole plus N-pole equals repulsion. When two north poles approach, they push apart. Second rule, S-pole plus S-pole equals repulsion. Two south poles also push apart. Third rule, N-pole plus S-pole equals attraction. North and south poles pull together. The diagram illustrates these interactions clearly. Notice how the arrows show force direction. This principle is fundamental because magnetic force decreases with distance squared, following an inverse square law. Now we examine the experimental method for investigating magnetic forces. This follows Cambridge IGCSE standards for practical work. The apparatus needed includes bar magnets with clearly marked poles, string for suspension, ruler for measuring distances, and iron filings for visualizing fields. The method consists of these steps. First, suspend one bar magnet horizontally using string so it can rotate freely. Second, bring the second magnet close to different poles of the suspended magnet. Third, observe and record whether attraction or repulsion occurs. Safety is paramount. The hazards include strong magnetic fields affecting electronic devices like phones and computers. Therefore, you must keep magnets away from all electronics and magnetic storage devices. The diagram shows the experimental setup with a suspended magnet and test magnet. Notice how the suspended magnet can move freely to show forces. Let's work through our first example. The problem states a student has two identical bar magnets. Predict the force when N-pole of magnet A approaches N-pole of magnet B. We are given two identical bar magnets with clearly marked poles. We need to find the type of force between the N-poles. Step 1, identify pole types. Both magnets have N poles approaching each other, so these are like poles. Step 2, apply the fundamental rule. We use the principle that like poles repel each other, which means identical poles push apart. Step 3, predict the result. A repulsive force will push the magnets apart when the N poles approach. Step 4, state the conclusion. N pole repels N pole with repulsive force. The answer is, repulsion occurs between like magnetic poles. Example 2 applies magnetic principles to real materials. The problem is, a magnet attracts an iron nail from 2 centimeters distance. The data shows a permanent magnet, an iron nail, and a separation distance of 2 centimeters. Now we analyze systematically. First, identify materials involved. We have a permanent magnet with fixed N and S poles, and an iron nail, which is a magnetic material. Second, determine magnetic properties. Iron is ferromagnetic, meaning it's strongly attracted to magnets and can become temporarily magnetized. Third, apply attraction principle. The magnet creates a magnetic field that extends beyond its physical boundaries. Fourth, explain force mechanism. The magnetic field induces temporary magnetism in the iron nail, creating attraction. The diagram shows the setup with the magnet, nail, and measured distance, illustrating how magnetic force acts across the gap. Advanced application skills help classify materials by magnetic properties. Let's examine 3 key skills for material identification. First, material testing procedure. When we test with a magnet, attraction indicates the material is magnetic. If there's no attraction, we identify it as non-magnetic material. This is a reliable test method. Second, magnetic materials identification. Iron, nickel, and cobalt are strongly magnetic, classified as ferromagnetic materials. Steel contains iron, therefore steel is also magnetic. These materials are attracted to permanent magnets and can be magnetized themselves. Third, non-magnetic materials recognition. Aluminum, copper, plastic, and wood are not attracted to magnets. These materials don't respond to magnetic fields in the same way. Understanding material classification helps predict magnetic behavior and is essential for practical applications in engineering and technology. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, what happens when S pole approaches S pole? Consider the fundamental rule about poles and predict the force type. Question 2 is intermediate level. It states, a magnet attracts a steel paperclip. Explain why. This requires you to apply concepts about magnetic materials and explain the attraction mechanism. Question 3 is advanced level. The question is, how would you test if an object is magnetic? This tests your experimental design skills and understanding of magnetic properties. For all questions, remember to show your reasoning clearly. Use scientific terms like attraction and repulsion, and explain the physical mechanisms involved. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how today's concepts apply in practice. In technology, magnetic levitation trains use repulsion between poles to float above tracks, eliminating friction for high-speed travel. The same repulsion principle we studied enables trains to reach speeds over 400 kilometers per hour. In medical applications, MRI scanners use powerful magnetic fields to create detailed images of internal body structures, revolutionizing medical diagnosis without invasive procedures. In engineering, electric motors rely on magnetic forces between permanent magnets and electromagnets to convert electrical energy into mechanical motion, powering everything from fans to industrial machinery. These applications show why physics matters. Career-wise, physics knowledge leads to electrical engineering designing power systems, medical physics, developing diagnostic equipment, and renewable energy creating sustainable technologies. The concepts you learn today become tomorrow's innovations. Let's review the solutions systematically. For question 1, the answer is S pole repels S pole because poles repel. This follows the fundamental rule that identical poles push apart with repulsive force. For question 2, we find that steel contains iron, making it a magnetic material attracted to magnets. The magnet's field induces temporary magnetism in the steel paperclip, creating attractive force. For question 3, the test procedure is, bring a magnet close to the object. If attraction occurs, the object contains magnetic material. If no attraction, it's non-magnetic. Now, exam success tips. First, always show your reasoning. Explain why magnetic forces occur, don't just state results. Second, use correct scientific terms. N-pole, S-pole, attraction, repulsion. Third, state fundamental rules clearly, like poles repel, unlike poles attract. Fourth, give specific examples. Iron, nickel, cobalt are magnetic materials. These strategies ensure maximum marks. Let's summarize today's lesson systematically. The key points to remember are, first, the fundamental pole rule, like poles repel, unlike poles attract. This means NN and SS combinations repel, while NS combinations attract. This rule governs all magnetic interactions and is essential for predicting forces. Second, magnetic materials iron, nickel, and cobalt are strongly magnetic. These ferromagnetic materials are attracted to permanent magnets and can become temporarily magnetized themselves. Steel, containing iron, is also magnetic. Third, magnetic forces act without physical contact through invisible magnetic fields. This demonstrates action at a distance, with force strength decreasing as distance increases. For further study, review magnetic material properties to distinguish magnetic from non-magnetic substances. Practice force prediction problems using the pole rules. The next lesson covers magnetic fields, which builds on today's work by explaining how magnetic forces are transmitted through space. Ensure you understand pole interactions before advancing to field concepts.